Okay, thank you for the invitation. Well, it's my pleasure to be here, just giving the last talk in this seminar. And today I want to talk to you about what is my vision of energy systems, but in particular, very particular power system. I've been working with power system for a while. Yes, my PhD was related with power system, but we are in very good time for seeing many changes to came to power systems. So I'm a system professor at the Skoltech, and let me start with these two pictures. On the left-hand side, so you have a picture of Fifth Avenue in New York, and you can see like, well, it's an old picture, and you can see here like most of the transportation was doing by horse cars. You can see like there is exception of two vehicles, like they are these combustion-based vehicles, automobiles. And this is in the left. In the left is like a long time ago. On the right-hand side, so you have also another picture, very long time ago. It's the same street in the same time of the year, but you have like the chain have it is totally changed. So you have all vehicles that you can see are combustion-based vehicles, except one horse car. Well, you can imagine like on the left-hand side, like, well, people from here, they were using horse cars for a very long time, like hundreds of years, and they changed from one picture to another picture, so you may think about there was a lot of years, but there was only 13 years, 13, and it happened pretty fast, only 13 years. So the way of transportation people in cities changed drastically, only 13 years. So every time that we see new technologies, we have what we call, we observe S-curve. And this S-curve, basically they have the name because they have a shape of S. And basically means like, well, at the very beginning, when we have a new technology, like combustion-based vehicle, so there is a very few adopters of these technologies, but suddenly there is a takeoff, and most of the person that they can potentially take this technology, adopt this technology, happens in a very short time of period. And then of course, the last part is always complicated to reach like 100%. But the thing is like, well, this kind of curve have been observed in many technologies. So if we look back to the last century, we have this kind of behavior in many technologies like telephones, TVs, PCs, coming back to the closest year, like 2000. So we see like tablets, digital cameras. So they have the same kind of S shape, but the difference is like instead of observing this adoption of technology in a range of years, tens of years, so you can see like maybe in like 5 years, so you are adopting a technology, like the adoption rate reached more than 80% maybe in like 5 years. So yeah, think about the smartphones, how far they were adopted. And this is important because in power system, there are already so many technologies that they will probably change the way that we see the operation of power systems. Let me go to the back, to the past. And many of you probably, you know, like, well, electrification was already classified like the greatest engineering achievement in the last century. Even if you compare with internet, rockets, or electronics, so electrification was the greatest one. So was classification for the National Engineering Academy of United States. And how looks like a power system? Very simplified way of understanding that. So you have some generations and generating units. You step up the voltage. You transfer this energy through some transmission lines, and then you step down the voltage and then consume in the last, let's say, commercial buildings or industry or even in your house. So this looks like this. So it is very sophisticated. So there are markets, but there are a lot of rules for controlling that. But basically, there's unidirectional. So we have a few hundreds of generators, and we have passive demands that they are only consuming. And this is more or less known every day. So statistically, we behave in the same way. There is a limited ICT technology, information or communication technologies, and usually it's at the transmission level, like a high voltage level. They used to be not storage, but there are some exceptions like pump and hydro storage, but there are a few of them. So if we see some photos of how it looks like, so well, this is kind of generators, and well, this is like probably last 10 years of life, last 20 years, so we are more used to see this kind of new generation, like wind farms. This is how it looks like generators, transformers, transmission lines, other transformers, and this is how it looks like the last consumption. And if you have studied electrical engineering, you have studied how works each of these devices, how to design these devices, how to control those devices, how to operate those devices. So all these things related with those devices have been already in the part of the electrical engineering academic plans. But I will show you like there is more than that, and especially in the coming years. So what is the presence of the power systems? So for the last 20 years, so basically it was the same. So power systems haven't changed too much, despite of all this technology that I'm telling you. But well, we have seen more and more renewable energies. This is a fact. Many countries, they are adopting quite large number of renewable energies. And we have seen small pilots that I will show you later about these small pilots. There are many new things that they are coming. And there are small pilots in many power systems just to understand how we can do. And when I'm talking about technologies, so there are many technologies that are right now at hand. And some of those technologies, they are still on a very good way of developing to have a very good result, a promising result in the next coming years. So let's think about like this Internet of the Thing. We have some controllers for very few that we can buy for a few dollars, and we can actually incorporate in the appliances in our home. So some of the what we call a smart today, everything is called smart. We can have a smart wash machine. We can have a smart smart refrigerators. But basically, those smart things are well, they have the capability of doing some simple control like on off, and to transfer some information. But also we have seen a lot of developments in batteries. So there is a lot of improvement. So this is why, for example, some electric vehicles are now very competitive. Or even you can buy some batteries that you can install in your house. There are other, this is a PMU, phasor measurement units. There are other technologies that are now being installed in power systems. That this is basically a sophisticated sensor that it gives us a lot of information. In 1 second, we can harvest about more than 100 samples data in 1 second. So we have also new technologies for coming like 5G. So 5G is already developed. So it's a matter of implementation. This allows to transfer a huge amount of data that we are not even aware how much data we can transfer for everything which is around us, everything which is consuming some electricity. Well, our cell phones is also some source of new technologies, artificial intelligence, or even cloud computing. So there are a lot of technologies that are ready. Some of these technologies, they are on the way of seeing quite a lot of changes in the next year. And most of these technologies somehow will form part of the power systems in the future. So what we are planning to see from now on, so we are planning to see, and some of this already is happening, is to see more and more distributed renewable production at the distribution level. So like household with PV panels that can actually inject into the main grid. Those kind of loads actually are stochastic. It means like, well, we have no control at all. So it depends on the weather conditions. We are planning to see like large number of non-controllable stochastic power sources, like this PV panel, but also electric vehicles. So we somehow, if we don't do anything, when an electric vehicle is connected to charge, so this is a load, and we don't have this control for now. So I will talk about this later. We will see more as energy storage connected to the electrical grids, a strong interaction between other networks like heat and electricity, gas and electricity, even transport and electricity. And there will be more and more extensive infrastructure in communication technologies at all levels, not only at the transmission, but also at the distribution. So we will see like the main role for controlling power system up to now basically have been done by generators, like big generators. And we will see like this is already moving to the demand side. So all this demand side actually will be will have the option to work together and to behave like generators. I will talk about a bit more. Well, power system is no more about devices, as we know, but it's the same like if we think about astronomy, is everything of astronomy is about the telescope. So we will see power system is not anymore just devices, it's more than that. So how I see the future, so I see future in different ways. So future will be globalization. Here I'm sharing with you a map of the telecommunication grid worldwide. You can see like most of the globe is very well connected, plenty of cables of connection for telecommunication. But you understand, or probably you know, like most of the country, they are not connected with the neighbor. We don't have a global grid on power, on electricity. And if a country is connected with the neighbor, basically it's very, maybe only one connection, which is kind of very limited in the amount of energy which is transmitted and the way of this is controlled. There are a few exceptions, like in Europe, but just think about like United States. In United States, you have one country, but there are many power systems. They are somehow connected, but still there are different ones. But there are people who are thinking like, well, a global grid actually provides some benefits, because you can understand like we have day and night always in the globe. We will have winter and summer always in the globe. So if you have some excedence of solar production, you can actually transfer to the other part of the globe when they are during the night, if you have the right transmission lines or the proper way of transferring that. So there is some many initiatives worldwide. So from Asia, so I can just really highlight this Asian supergrid. There are others that they are involved in more countries. There is a institution called HATECO, which also is studying about just to understand how will look like the global grid in 2050. They are running some feasibility studies. And there is, if you are not familiar with SIGRE is basically similar to IEEE, but they are running some working groups. There are some working groups working in this concept of the global grid. So there is a lot of benefits for interconnecting the many countries at the same time, but still there are some political and regulatory issues that they are making this complicated, but feasibility studies are there. So the future also is integration. And integration, it means like electricity network actually is linked with other network, like for example, heat network. Here in Russia is very important, district heating. And the same kind of generator we are using for providing heat, they are used for providing electricity. So there are strong links for that. But the way that we are coordinating them probably can be very, they are not really strongly integrated, but there are a lot of possibility for bringing flexibility from other networks to the electricity network. The same for gas network. Now we are, well, there are a lot of discussion about hydrogen, but there are not only integration with energy carrier, but also with transportation. So thinking about in a future with plenty of electric vehicles, a coordination of the of transportation, like routing plus electricity network, where to charge, when to charge, actually can bring some benefits to the power grids. And this is something that we will see more and more. But the future also is decentralization. And why decentralization? So there are new actors now coming to the power grids. This is a new from 1 year ago. Like Amazon decided to buy 100,000 of electric vehicles for delivering last mile delivery. Basically, well, this is 100,000. So they see like they can get some competitive advantage using these electric vehicles instead of classical vehicles. There are other startups like Waymo. You probably hear about Waymo. So Waymo is a startup which is intended to provide services of taxi or transportation services with electric vehicles with no driver. So there are now they are in Portland, so they are running some pilots still. Well, there is a few years until this happens. Tesla also is thinking now to provide transportation service. So there are many companies that they probably will be providing new ways of business in transportation. And many of those companies actually are looking to these electric vehicles. And electric vehicles are strongly connected with power grid. I will give you some examples. Of course, so the new actors are like cities, Shenzhen in China. So both like 3 years ago, the 16,000 electric buses. They basically replace all buses by electrical ones. And this is kind of a pretty big achievement. In Chile, they replace kind of about 20% of electric buses in Santiago, the capital of Chile. And for 1 year, they were running some collecting data, and they already proved by facts that running electric buses is cheaper than running the classical combustion-based buses. So they are more competitive. The electric ones are more competitive. So you can understand like many cities will think to replace those buses for new ones, electrical ones, because they are more competitive in terms of cost. Well, this is how it looks like this S-curve. This is from 2 years ago, one and a half year ago. We see some countries actually are reaching like even 35% of new vehicles are electrical ones. So the new purchase of vehicles are electrical ones. So we see like many countries actually are in this takeoff part of this S-curve. So when we reach like 80%, actually will be quite a challenge for power systems. And why is it challenging to have electric vehicles? So like this is kind of some rough numbers. Like let's imagine that you have electric vehicle, typically 100 kilowatts of power when you are charging. If you think like you can discharge, let's say 100 kilowatts. Well, a nuclear power plant is more or less roughly 1 gigawatt. So 10 vehicles, electric vehicles charging at the same time is 1 megawatt. 10,000 of electric vehicles is equivalent to 1 nuclear power plant. And 1 million of electric vehicles is equivalent to 100 nuclear power plants. So, and those electric vehicles usually are connected to the distribution grid, to the low voltage grid, which is not pretty common to have very reinforced distribution grid. And 1 million vehicles, electric vehicles are many or not? For sure, 100 nuclear power plants, this is a lot of nuclear power plants, but 1 million. Yeah, okay, let me give you also some information about the energy. This is about power, but energy. So these typical electric vehicles like Tesla Model 3 consumes for every 100 kilometers about 15 kilowatt hours. So in average, some average customer use the vehicles about 15,000 kilometers a year. So the annual consumption of one electric vehicle is about 2.25 megawatts. So let's say 1 million of electric vehicles in terms of energy is like 2,200 gigawatts. So 4 million of electric vehicles is equivalent about 1% of the annual consumption in Russia. 1% actually could be pretty important increase. So remember, just to have a rough idea for the people who live in Russia, Russia have about 51 millions of vehicles. So if we have like 20% of them electric ones, so it will be 2.3% of the total demand in energy. There are 0.4 millions of buses, 7.9 millions of commercial vehicles. So if all of them becomes electrical ones, so it will be 2% of the total demand. But let's go just Moscow, where this is the city where I'm living now. So Moscow has on the streets every day have 3.5 millions of electric vehicles, despite there are more registered vehicles. But only 1% of these electric vehicles is connected at the same time. 1% of these 3.5 million. So I'm not saying all of them they will become electrical one. Let's say like maybe 5% become electric vehicles. If 1% of these 3.5 million is connected to the at the same time, they're charging simultaneously. This means like 3.5 gigawatt. It means like 3.5 nuclear power plants connecting at the same time. It's a ramp, pretty high ramp. And this actually can bring a lot of problems for the power system. So we can see like, well, there are problems. So what can we do? So there are some initiatives like in Spain, the operator of the grid actually started to monitor what is happening with the electric vehicles. So just, they do not do any kind of control, but they just monitor. So they open a new control center in Spain, which actually is not control because they are not controlling anything, but they just monitor what is going on with the consumption of electric vehicles when they are connected. So this is kind of first initiative, but we can do more, and we can do what is called smart charging. And smart charging basically is decide when should we be charging and which is the best moment for charging. And this is the typical daily load profile. So this here, this is a base load with no electric vehicles in one system. We have this peak at the night when people come home and then switch on the light, start to cook, watch TV or watch Netflix, whatever. But at the same time, if you are going back home, so this is by simulation, so you can expect like, depends on how much electric vehicle you have, but basically all of electric vehicles will be charging during the night. So you come to home and then you connect your electric vehicles and then you put the electric vehicle on charging mode. So if you do that, so you will expect to have a very high peak of power capacity. And this actually can be a very important problem in the system. So smart charging basically is understand how you can control the charging by filling some valid periods and not overloading this peak. So if we do, for example, coming back to the example of Russia, we have these 7.9 millions of commercial vehicles. We do not do like smart charging, means like, well, we will need to reinforce the generation capacity in almost 800 nuclear power plants, the equivalent of 800 nuclear power plants, just for having sure that you are always able to provide this power when it's needed. But if we do smart charging, so we can just reinforce the system with the equivalent of 3 nuclear power plants. Well, the energy is the same, but it's in different moments of time. There are different ways of doing the smart charging. So I think I will, well, one direction or maybe two directions. I think I will jump. And there are countries that actually they are what is called vehicle to grid. So if you are using your electric vehicle for providing some services to the grid, so you can get remuneration for that. Some countries like Denmark, they already have proof that you can get like 1,400 euros a year, more or less. In Spain and Portugal, so you can have about 600 euros a year, just for saying like, well, when I have my electric vehicle connected to the grid, I allow the system operator to use this battery for providing some services like frequency regulation, etc. So something even more recent, in this March 2020, Tesla launched a new business, what is called Autobidder. And Autobidder basically is they are algorithms. They are using what is called Tesla power packs. Basically, it's batteries. It's not batteries from your car, but this is battery that you can buy and keep in your house. And they have a way of automatically bid to the real-time markets in electricity and to get profit from out of that. And this is already working. It's working in South Australia. And now in June, actually it started to operate in Europe. Just to, if you are owner of this battery that you have installed in your house, you can actually contract with Tesla this automatic bidding. It doesn't need to be a Tesla power pack. I think like there are other brands or other companies that they can serve like a battery for the same purpose. So we see also in every of our house or commercial buildings what is called thermostatically controlled loads, TCLs. Like let's say like refrigerators, these heaters, these boilers. So they are basically thermal loads. They have some inertia, and we can make use of this inertia. So let me give you an example. Like this is a typical, how typically works. Like this is a radiator, like this a heater, and usually you have a thermostat which control when the heater is on and when the heater is off. So and then this thermostat basically is a on-off control, depends on the range of the temperature. So if the temperature is over some minimum one, so if drops over some minimum one, so the signal of temperature actually makes this on, and then there is a consumption of power here. So the temperature in the house start to increase because you are heating the house or the room until you reach some maximum. When you are in the maximum, so this signal actually is say like, well, just switch off this heater, and then the temperature start to decrease. And then you have this kind of cycling behavior with this classical thermostat that everyone has, or at least you have seen. But there is something very interesting here. Like, we can somehow measure frequency at every socket. So frequency is something that it's very simple to measure. And if you measure frequency here, even you can make some response. So you can make this a little bit smart, and then say, well, if the frequency is decreasing, so you need to switch off your loads. And if you have thousands or millions of loads, they are responding at the same time. So you can make some frequency control for the main grid. So this very, very little control and very little load can participate in an aggregation of many others, and to see them like a generator who is making frequency regulation. Well, you can also understand like this looks like a battery because you have some frequency, and then you do, meanwhile you keep temperature between some limits, so everything is okay. But there are some problems with this. Of course, this is some of the challenges when you have many of these elements. So this is a simulation that we have run here. So starting with random temperature between 20 and 24 for 50 houses, and responding to some real frequency signals. And we see after a while, so they start to synchronize. And this is one of problem when we have many of these small devices responding at the same time. This is called also rebound effect. So but still there are some people who are looking how we can actually deal with that in such a way that we can include thousands of those houses as a response. And this idea is pretty nice because if you think about house, and this is a TCL, thermostatically controlled load, everything is already in place. So you don't have to invest anything. You maybe need something like this, like some smart device, which costs a few dollars, and can measure frequency, and then you can respond to that. So this is very cheap. You don't need to buy a Tesla wall or any kind of battery to make this kind of response and to start to offer some services to the grid. Okay, so you may imagine like, well, at the distribution level, so probably we will find many of these kind of loads, let's say smart loads, a lot of renewable generation. This is the things that we are observing more and more. And if we are able, let's say we are able to aggregate and to control and to coordinate all of them simultaneously, so we can see like this is the typically PQ, or sorry, this is a active and reactive power at the substation, how much active and reactive power this distribution grid is consuming. But if you have all this flexibility in connecting here, so you can imagine, well, this active, you can consume in some moments more, even you can decrease the consumption sometimes. But even during some moments, you can even go to this left-hand side, which is the active power is negative, means like instead of consuming from the transmission level, so you are injecting. So this distribution grid, if we are able to aggregate all these devices, so it can be actually work like a generation mode. Well, and in local, also in distribution level, so we are seeing a lot of direction of what is called sharing economies or peer-to-peer markets, but there are a lot of initiative on that, how you sell energy to your neighbor, how much your neighbor should pay for that. But I asking you a question like, if probably you don't know, maybe you have some belief, like, is it legal to sell energy to your neighbor in your country while being connected to the grid? Well, most of the countries is illegal. So even if you have a PV panel at your house and you have excess of energy and you want to sell this excess of energy to your neighbor, so probably this is illegal in most of the countries. There are some countries that already they are making some regulation, and then you can aggregate some community for doing that. Yeah, and there are plenty of initiatives. So here is a very good link. I can share later these slides. Plenty of initiative of how we can startups on microgrids, not only for peer-to-peer, but also for creating these local markets of these microgrids. And the regulation is important also. The question, can you do that? Yes, maybe you have technology, maybe you have algorithms, maybe you have the transaction marketplace, but if the regulations say that, no, you cannot do that, so you will be against the law. So regulation is important, and many countries are actually adapting to the new changes. Well, California is exceptional for that. It's kind of some steps away. If you want to see what is going on in power system, you can go to California to understand what is happening there. But there are many countries they don't have any regulation, but most of the countries they are studying what will be the impact of that. So even if they don't have regulation, so they are studying what will be the impact of local markets in these classical power grids. Well, the future of power system also is full of mathematical challenges. The first one, I call variability. We have seen like renewable energy that sometimes they are called non-conventional, but I don't like this name anymore because from 2012, the overall investment in renewables was larger than the conventional one. So from 8 years ago, renewables are actually more conventional than the classical one, right? So, but renewable have very particular feature, like which is non-dispatchable. And this is an example of what happened in a wind farm. Even you are aggregating many windmills, and from one day to another day, so this is kind of a mesh. So if you see like here, you have 24 hours, and this is the output in megawatt of this wind farm. This is in California. It's quite old, but this applies for everyone. From one day to another day, this is pretty different. It's complicated to forecast what is the output of the wind. And if you are taking some average, actually that's not very meaningful. This is typically called a spaghetti chart because it looks like a spaghetti dish. Okay, there are other challenges on mathematical methods. And those challenges, I will show you one example, like they are motivated by the speed up of hardware and software in the last 25 years. So in the last 25 years, we have seen like hardware multiplies by 2,000 times the capabilities of doing computation. But what's most important, like softwares and algorithms, not only software, also algorithms, they actually scale up to 2 millions faster, right? So if you multiply hardware and software and algorithms, so you have about 10 to the 9 times faster. You can solve, you can imagine that problems that takes maybe years to solve, like 25 years ago, now it takes seconds. And this capability actually are improving the way that we are operating the systems and the way that we can reduce cost. And this is a real example, like in California, again, it's coming California. So they changed the way that the method of solving one problem is called unit commitment. But the problem is the same, the formulation is the same, but the algorithm that is solving that was changed. It was in 2009, because at this time, so there were more capabilities, so they were able to solve with another method, which improved the solution process. And just by this change, so they are saving every year $23 million, right? So it's a lot, but that's changing by the algorithm, they are solving that. The problem is the same, the formulation is the same, so just the algorithm for doing that. And right now, so today, so we are living in a very exciting moment. So if you study electrical engineering, so probably you are familiar with this alternative current optimal power flow, or ACOPF, which this is basically the physical laws of power system, which are very nasty. So they are non-convex, and engineers, we make a lot of assumption and simplification for have some linear approaches of that. But when we are linearizing, or when we are approaching things, so we are missing accuracy, and then this costs more for the overall system. So in the last 5 years, there were a lot of new research articles which provide new formulation of that, closer and closer to this original non-linear non-convex formulation. And in fact, like more than 1 year, like 1 year and a half, or even 2 years, of the ARPA-E from United States, they launched a competition which is called grid optimization, which in the first challenge is already over. They give $4 million in prizes, and just to improve, they give you the problem, and you just need to give an algorithm for solving that. The best algorithms, the top 10, so actually are getting prizes for that, and up to 4 million in prizes. And now they are in the second challenge, so they are giving us 2.3 million. So you can think about, wow, this is too much money for those challenges. This is a computational challenge. If you have been working in hackathons, this is kind of hackathon. It took 1 year, of course, so it's kind of a very large hackathon, but let me go back. Remember, this is the saving only in California, 23 million for changing this algorithm. And this is like peanuts. And why they are launching this competition right now? Because all these new findings during the last 5 years that they believe they can actually take part on the new way of operating power systems. And I think I will finish soon. So challenges also are coming from going from data. We are expecting to have a lot of data, not only to information, but also to decisions. And the last one is much more important. Remember I mentioned about these smart homes and all smart devices that we are expecting to have at home. Those devices are creating data, and those data actually have some value. But also at the transmission level, there are many of new sensors, or at least a new generation of sensors, it's called PMUs, that they are taking hundreds of samples per second. And this is a lot of data. Actually, with this information, we can actually understand better the dynamics of the system. So what to do with this data? Well, you can do with this data, well, you can get data, you can create some models and you can make predictions. And this is typically what is done in machine learning, artificial intelligence, statistics, right? So you have plenty of data, you provide a model, and then you have some predictions. So different type of prediction, classification, etc. Well, this is good. We have seen a lot of improvements on how to distinguish between Chihuahua and muffins. Go competition, or we can actually predict what will be the generation power of the windmill like next 24 hours, right? But there are other kind of problems which are probably more interesting in power system, is like decisions. So how much should produce a generator tomorrow? Or when should we start to make maintenance of those windmills? And those are decisions. They are not only predictions. So prediction will be when a windmill will fail, but decision is when is the best moment for doing this maintenance. And usually this model, this way of making the decision is like, well, we have a model with some parameters, and they use what is called optimization or mathematical programming. So the idea, and right now, is something like, well, there's a lot of things to do. It's called analytics. It's just how you go from data, you are collecting data, to decisions, right? And yes, I will finish here. Like, this is some of the challenge, and I will finish only with one takeaway. I don't want to extend more, and then we can have time for discussion. And more than a takeaway is kind of a sentence. Like, I think, like, well, likewise, many of the improvements of electric cars will come from improvement in the operating systems and the software. So we are expecting, like, electric car basically are a machine full of sensor and software. So most of the improvements will come from that. So in power systems, most of the improvement will come from algorithms that will operate and control them. This is kind of a takeaway. This is very general. We have now time for discussion. First, before going to the Q&A, so I want to introduce you to my research group, which is Power Market Analytics, Computer Science and Optimization. You have more information here in this link. And yes, you can see what we are doing, what are our research lines, how you can join us, etc. And yes, thank you so much for your attention, and I'm happy to answer questions.